Hey there, tonight we're going on a journey not into outer space but into something just as vast and mysterious, the skies right above us. We'll explore the soft hum of morning fog and the graceful dance of winds. It's a calming exploration of atmospheric wonders, perfect for winding down. If you enjoy this journey, please take a moment to like this video and subscribe to The Sleepless Scientist. For centuries, humanity has gazed upwards, wondering about the vastness above. But what if the sky isn't just a distant expanse? What if it's something we are constantly immersed in, yet rarely truly notice? Imagine for a moment that we live at the bottom of an invisible ocean, not water, but air. This vast, swirling fluid, our atmosphere, envelops our planet hundreds of miles into space. This ocean of air is our lifeblood. It provides the oxygen we breathe, shields us from harmful radiation, and acts as a planetary blanket, regulating temperature. Without it, life would not exist. For early humans, the sky was a source of both wonder and profound mystery. The sun, moon, and stars moved predictably, yet weather felt unpredictable, even divine. Thunder and lightning, fierce winds, and devastating floods inspired awe and fear. To explain these powerful phenomena, early civilizations wove intricate myths, attributing weather to the whims of gods. Around 450 BC, the Greek philosopher Empedocles proposed a structured idea. Everything, including the sky, was composed of four fundamental elements: earth, water, air, and fire. In this view, air was not merely empty space, but a tangible, if invisible, substance. It was seen as a light, expansive element, distinct from solid earth or flowing water. This elemental theory, while not scientifically accurate by modern standards, marked a crucial philosophical shift. It began to treat the atmosphere not as an ethereal void, but as something composed of matter. This fundamental idea that air was a substance laid the groundwork for future scientific inquiry. It transformed the sky from a realm of pure mysticism into a potential subject for rational investigation. Even without advanced tools, ancient observers noted patterns. They charted prevailing winds, understanding their power for sailing and their role in bringing rain or drought. The formation and movement of clouds were also noted, though their true nature remained elusive. Were they simply condensed water vapor or something more complex? Some early thinkers even considered the atmosphere as the breath of the earth, a living, responsive entity that inhaled and exhaled, influencing life below. Yet the idea that air had weight, that it exerted pressure, was far from intuitive. It felt weightless, formless, an absence rather than a presence in daily experience. The very concept of a vacuum, a space devoid of air, was a contentious topic for centuries. If nature abhorred a vacuum, then air must always be present, even if unseen. The shift from philosophical speculation to empirical measurement was slow but inevitable. The desire to understand rather than just explain began to take hold. While the four elements provided a framework, they couldn't explain the subtle complexities of weather. Why did clouds form? Why did rain fall? The answers lay deeper in observation. The crucial realization was that this invisible ocean wasn't just a concept. It was a physical mass exerting pressure on everything within it. This was a profound, paradigm-shifting idea. Early experiments, though simple, started to reveal air's tangible properties. The collapsing tin can, the suction of a plunger, these everyday observations hinted at air's hidden power. This period marked the boundary between ancient mystical explanations and the dawn of scientific inquiry. The invisible ocean was slowly revealing its true, measurable nature. Scientists began to observe the subtle forces at play, the way smoke drifted, the way leaves rustled, the way a flag billowed in the wind. These weren't just random occurrences. The transition from philosophical discussion to the physics of air was slow, painstaking work, driven by pure curiosity and a desire to quantify the world around them. This shift laid the groundwork for meteorology, the science of weather. It transformed the unpredictable skies into a system that, eventually, could be understood, even predicted with careful observation. So, Chapter 1 concludes with this fundamental understanding: we live within a vast, physical atmosphere. This realization, centuries in the making, is where our journey into the swirling skies truly begins. The idea that we lived at the bottom of an invisible ocean was profound. But how did this ocean exert its presence? For centuries, practical observations hinted at an unseen force, yet its true nature remained elusive. It was in the 17th century, a time of burgeoning scientific curiosity, that this mystery began to unravel. One of the first clues came not from a grand theory, but from a very practical problem. Well diggers in Italy during Galileo's time found that their suction pumps could not lift water higher than about 32 feet, no matter how powerful the pump. This was puzzling. According to the prevailing wisdom, nature abhorred a vacuum. If a pump created a void, water should rush in to fill it, theoretically rising to any height. Yet there was this undeniable limit. Galileo himself pondered this anomaly. He recognized that the old adage, while seemingly true in many contexts, failed to explain this specific observation. The water simply would not rise beyond that mystical barrier. He suggested a concept of a force of vacuum that was finite, a kind of resistance that could only support a column of water up to a certain weight. It was a step towards understanding, but the true mechanism remained hidden. It was Galileo's brilliant student, Evangelista Torricelli, who took up the challenge. He reasoned that if the force wasn't pulling the water up, perhaps something else was pushing it from below. Torricelli proposed a revolutionary idea. The air itself, this invisible ocean we swim in, had weight. This weight, he theorized, exerted a pressure on the surface of the water, pushing it up into the evacuated pump. To test this, he needed a fluid much denser than water, so the column would be manageable in a laboratory. Mercury, with its silvery sheen and immense weight, was the perfect choice. In 1643, Torricelli prepared his experiment. He took a long glass tube, sealed at one end, and filled it completely with mercury. It was a simple setup, yet profoundly insightful. Then he carefully inverted the mercury-filled tube into a basin also containing mercury. The moment of truth arrived as the heavy liquid began to descend. Instead of emptying completely, the mercury column settled at a height of about 76 centimeters or 30 inches. Above the mercury, a distinct, empty space formed. This space, the Torricellian vacuum, was truly empty, a radical concept at the time. It proved that nature did not abhor a vacuum universally. It could exist under certain conditions. Torricelli concluded that the column of mercury was held up not by a force of vacuum, but by the weight of the air pressing down on the mercury in the basin outside the tube. The two forces were in balance. This was the first direct, measurable proof that the atmosphere had weight and exerted pressure. It was a monumental shift in understanding our invisible ocean. News of Torricelli's experiment quickly spread across Europe, captivating other brilliant minds. Among them was the French mathematician and philosopher Blaise Pascal. Pascal reasoned further: if the atmosphere truly had weight, then its pressure should decrease as one ascended higher, just as the pressure in an ocean decreases closer to the surface. To test this elegant hypothesis, Pascal devised a grand experiment. He would send a barometer up a mountain. The Puy de Dôme, a prominent peak in central France, was chosen as the ideal location. In 1648, Pascal's brother-in-law, Florin Peyrier, meticulously prepared for the ascent. He carried a Torricellian barometer, carefully calibrated, along with a spare for comparison. The journey up the volcanic peak was arduous. The air grew thinner, the landscape more stark, but the scientific purpose drove them onward. Every step was a step higher into the atmospheric column. At the foot of the mountain, Perrier took the first precise reading. The mercury stood at its expected height, a testament to the weight of the air above the valley. Upon reaching the summit, the air was crisp and thin. Perrier carefully set up the barometer again and observed. The mercury unmistakably had fallen. Comparing the readings, the difference was clear. The mercury at the summit was significantly lower than at the base. This proved beyond doubt that atmospheric pressure decreased with altitude. Pascal's elegant experiment solidified the concept of an atmospheric column, a measurable entity whose weight varied with height. The invisible ocean now had depth and density. This profound understanding of air pressure opened new doors. It explained why mountain climbers struggled to breathe and provided a fundamental piece of the puzzle for understanding wind, weather systems, and the very dynamics of our skies. With the weight and varying pressure of air now understood, scientists could begin to explore how this gentle breath truly moved, how it shaped our world, and how these invisible forces give rise to the winds and the clouds we see. Our journey now moves from static pressure to dynamic motion. The revelation of air pressure was a profound step, but understanding that air had weight was only the beginning. The next great mystery was motion. How did this invisible ocean move? Why did winds blow with such predictable patterns across vast distances, shaping trade routes and influencing continents? For centuries, sailors had known these great currents of air. The trade winds, steady and reliable, pushed their vessels across oceans. But their very consistency begged a scientific explanation, not just practical observation. In the late 17th century, the English astronomer Edmund Halley, famous for his comet, turned his keen observational skills to these atmospheric mysteries. He began to systematically map the prevailing winds reported by mariners. Halley proposed that the sun's heat was the engine. He reasoned that intense solar radiation near the equator caused the air to warm, expand, and rise, creating a region of lower pressure. This rising warm air would then flow poleward, cool, and descend in cooler regions, creating a vast circulation cell. The cooler, denser air would then flow back towards the equator, completing the loop. Halley's model was a significant step, explaining why air moved from high to low pressure. Yet, it couldn't fully account for the observed easterly direction of the trade winds. If air simply flowed from poles to equator, it should blow directly north-south. It was George Hadley, an English lawyer and amateur meteorologist, who refined Halley's concept in 1735. Hadley introduced a crucial missing piece, the Earth's rotation. Hadley realized that as air moved from the equator towards the poles, or vice versa, the Earth's spin would deflect its path. Air moving towards the equator from higher latitudes would lag behind the faster rotating surface, creating the easterly trade winds. This concept, later formalized as the Hadley cell, provided a compelling explanation for the broad patterns of global circulation. It was an elegant blend of thermodynamics and planetary mechanics. Still, a deeper, more universal principle was needed to explain this deflection across all scales of motion, not just global wind belts. The true mathematical foundation for this effect came nearly a century later. In the 1830s, the French mathematician Gaspard Gustave Coriolis was studying the mechanics of rotating systems, particularly the efficiency of water wheels and machinery. His work was purely theoretical, focused on the physics of motion. Coriolis described an apparent force that acts on objects moving within a rotating frame of reference. This force, while not a true push or pull, arises from the inertia of the moving object combined with the rotation of its environment. Imagine trying to draw a straight line from the center of a spinning merry-go-round to its edge. From the ground, your hand moves straight, but from the perspective of someone on the merry-go-round, the line appears to curve. This Coriolis effect meant that in the northern hemisphere, moving objects, be they air currents, ocean currents, or even cannonballs, would be deflected to their right. In the southern hemisphere, the deflection would be to their left. When applied to the vast scale of the atmosphere, Coriolis's mathematical principle provided the missing piece for understanding global wind patterns. It explained why air didn't simply flow in straight lines between high and low pressure. The great wind belts, the swirling patterns of storms, the very direction of the trade winds, all were now understood as a dance between pressure gradients and the Earth's relentless spin. It was an invisible hand guiding the air. As these theoretical understandings deepened, so too did the tools for observation. Simple wind vanes had long indicated direction, but quantifying wind speed required new ingenuity. The invention of the cup anemometer in the mid-19th century allowed for more precise measurements of wind speed. No longer was it just a qualitative breeze or gale, but a measurable quantity. With improved instruments came the ability to create early weather maps, charting wind direction and speed across regions. This systematic collection of data revealed the intricate, dynamic nature of atmospheric currents. Scientists began to see not just isolated gusts but vast, interconnected systems of air movement, driven by the sun's energy and shaped by the planet's rotation. The invisible currents were finally being charted. From Halley's initial observations to Hadley's elegant refinement, and finally Coriolis's profound mathematical insight, the graceful dance of wind began to reveal its underlying choreography. This understanding of wind was more than just academic curiosity. It revolutionized navigation, improved agriculture, and provided a critical piece for understanding the broader weather system. The air, once perceived as a simple, static element, was now known to be in constant, complex motion, a fluid responding to the Earth's heat and spin. These invisible currents were powerful architects of our world. With the weight of the air understood and its global movements charted, scientists now possessed the fundamental principles to explore the next great atmospheric mystery: how this moving air transformed into the visible wonders of clouds and rain. Our journey now turns from the invisible currents of wind to the delicate, yet powerful, process by which these currents gather moisture, lift it high, and paint the sky with the promise of precipitation. The dance continues, becoming visible. The air, now understood as a dynamic, moving entity, carried more than just pressure and wind. Within its currents flowed another invisible component: water. This water, in its gaseous form vapor, was the quiet architect of the sky's most dramatic transformations. For centuries, the presence of moisture was felt: the oppressive stickiness of a humid day, the crisp dryness of a desert night. But quantifying this invisible water, understanding how much was truly present, was a challenge for early atmospheric scientists. Water, unique among common substances, exists naturally on Earth in all three states: solid, liquid, and gas. In the atmosphere, it's primarily as an invisible gas, water vapor, dispersed amongst the nitrogen and oxygen. The amount of water vapor the air can hold is not limitless. It depends heavily on temperature. Warmer air has more energy, allowing its molecules to move faster and hold more water vapor before it becomes full. When air holds the maximum amount of water vapor possible at a given temperature, it is said to be saturated. Any additional cooling or addition of vapor will cause the invisible gas to change form. This critical temperature at which the air becomes saturated and condensation begins is known as the dew point. It's the temperature at which the air's invisible water vapor is compelled to reveal itself. Observations of dew forming on cold surfaces like grass in the morning or a chilled glass on a warm day provided early, intuitive clues about this process. The air around the cold surface had cooled to its dew point. Early instruments like the hair hygrometer, which used the property of hair to change length with humidity, allowed scientists to begin quantifying the moisture content in the air, moving beyond mere sensation. The moment water vapor condenses is the very first step in the birth of a cloud. But why does it condense into tiny droplets rather than just a uniform sheet of water? Pure water vapor, even when saturated and cooled, struggles to condense on its own. It needs a surface, something to cling to, for the water molecules to gather and transition from gas to liquid. This is where the invisible, often overlooked, inhabitants of our atmosphere become crucial: microscopic particles known as condensation nuclei. These are the tiny seeds upon which clouds are sown. These nuclei are everywhere: dust blown from deserts, pollen from plants, sea salt from ocean spray, soot from fires, even tiny sulfuric acid particles from volcanic eruptions. They are the constant, unseen companions of the air. Without these countless minuscule platforms, even saturated air would struggle to form clouds. The water vapor would remain a supersaturated gas, waiting for a surface to coalesce upon. As moist air rises and cools, it eventually reaches its dew point. At this precise moment, water vapor molecules begin to attach themselves to these condensation nuclei, one by one. These growing clusters of water molecules form incredibly tiny liquid water droplets, often less than 1/100th of a millimeter in diameter. Individually, they are invisible to the naked eye. But when billions upon billions of these microscopic droplets form in a concentrated mass suspended in the air, they scatter light. And it is this scattering of light that makes the cloud visible to us. For centuries, clouds were described poetically, but without a common language. A breakthrough came in the early 19th century when a meticulous observer sought to bring order to the sky's chaotic beauty. Luke Howard, a British chemist and amateur meteorologist, was fascinated by the ever-changing forms above. He recognized the need for a systematic classification, something enduring and universally applicable. From his home in London, Howard spent years observing, sketching, and categorizing clouds. He sought to identify fundamental forms that represented the different ways water vapor manifested in the sky. In 1803, Howard published his groundbreaking essay on the modifications of clouds. He introduced Latin terms, drawing on their universality to describe the three primary forms: cirrus, cumulus, and stratus. Cirrus, meaning curl of hair, described the wispy, high-altitude clouds. Cumulus heap denoted the puffy, cotton-like clouds. Stratus layer referred to the flat, sheet-like clouds covering the sky. He also introduced nimbus, meaning rain cloud, to denote any cloud from which precipitation was falling, often combined with the other forms, like cumulonimbus for a towering thunderstorm cloud. Howard's system was simple, elegant, and profoundly influential. It provided a common vocabulary for meteorologists and observers worldwide, allowing for consistent communication about the sky's ever-changing canvas. With a shared language, scientists could now correlate specific cloud types with different weather phenomena. The appearance of cirrus often hinted at approaching fronts, while cumulus suggested fair weather or, if growing, potential storms. The quiet birth of clouds from invisible vapor to visible forms was now understood. But these ethereal structures held a greater secret: the power to release their condensed moisture back to Earth. Our journey next explores how these tiny droplets grow, collide, and eventually fall as rain or snow, completing the atmospheric cycle. Chapter 4 concluded with the quiet birth of clouds, those ethereal masses of countless tiny water droplets. But these droplets, often just a few micrometers across, were far too small to fall as rain. The question remained, how did these microscopic specks grow large enough to overcome the air's resistance and descend to Earth? For centuries, rain was simply a phenomenon, a gift from the heavens. But by the early 20th century, atmospheric scientists began to delve into the microphysics of clouds, seeking the precise mechanisms by which these tiny cloud particles transformed into the gentle, life-giving drops we know. The challenge was immense. How could one study processes occurring miles above the ground within clouds at a scale invisible to the naked eye? Patience, ingenious instrumentation, and careful deduction would be the keys to unlocking this atmospheric secret. One primary mechanism for droplet growth, particularly in warmer clouds found in tropical regions, is known as the collision coalescence process. It begins with the simple fact that not all cloud droplets are born equal in size. Some droplets, perhaps forming on larger condensation nuclei, are slightly bigger. These larger droplets, subject to the same gravity as their smaller counterparts, begin to fall, albeit very slowly, through the cloud. As these slightly larger droplets descend, they inevitably encounter the more numerous, slower-moving, smaller droplets in their path. The crucial step is the collision. They bump into each other. But collision alone is not enough. They must also coalesce or merge. If the conditions are right, the surface tension of the water allows the two droplets to combine, forming a single, larger droplet. This process is a chain reaction. The newly enlarged droplet now falls even faster, increasing its chances of colliding with and sweeping up more small droplets. It's like a snowball rolling downhill, growing with each turn. Within a matter of minutes or perhaps an hour, a cloud droplet that started as a tiny speck can grow 1,000,000-fold in volume, becoming heavy enough to fall as a warm raindrop, a testament to this efficient merging process. However, the collision coalescence process doesn't account for all rain, especially in mid-latitude and colder regions. Here, another, more intricate mechanism dominates, the Bergeron-Feindeisen process. This process, independently described by Tor Bergeron and Walter Feindeisen, relies on a subtle but profound difference in the properties of water. The vapor pressure over ice is lower than over supercooled liquid water at the same temperature. In clouds where temperatures are below freezing but above approximately -40°C, both supercooled water droplets, liquid water existing below its freezing point, and ice crystals can coexist. Because the vapor pressure over ice is lower, water vapor molecules in the cloud are more attracted to the ice crystals than to the supercooled water droplets. It's a subtle but relentless draw. This means that ice crystals grow rapidly, absorbing water vapor directly from the air, which in turn causes the supercooled water droplets to evaporate to replenish the vapor supply. The ice crystals steal the moisture. This rapid growth makes ice crystals much larger than the surrounding water droplets, leading to their eventual fall. As they descend through warmer layers of the atmosphere, they often melt, becoming raindrops. So, whether born from collisions in a warm cloud or from the icy embrace of the Bergeron-Feindeisen process, a droplet, now large enough, begins its journey. Gravity, finally, becomes the dominant force. The descent is a complex ballet of physics. Air resistance, temperature changes, and even interactions with other falling droplets shape the raindrop's path. Sometimes it falls as a perfect sphere, other times as a slightly flattened teardrop. If the atmosphere below remains cold enough, the ice crystals may never melt, falling instead as snowflakes, each unique, a testament to the intricate dance of water molecules and temperature. The whisper of falling rain or the gentle descent of snow shapes our world. It replenishes rivers, nourishes crops, and carves landscapes, completing a vital part of Earth's water cycle. Understanding how rain forms from the smallest cloud droplet to the heaviest downpour has been a triumph of patient observation and microscopic analysis. It reveals the hidden intricacies within seemingly simple weather phenomena. The insights gained from studying collision coalescence and the Bergeron-Feindeisen process were not just academic. They advanced our ability to predict precipitation, crucial for agriculture, water management, and disaster preparedness. This knowledge also laid the groundwork for understanding cloud seeding, a controversial but fascinating attempt to influence precipitation by introducing nuclei into clouds to encourage droplet growth. From the soft hum of the morning fog to the gentle fall of rain, we have traced water's journey from invisible vapor to a tangible blessing. Each stage, a delicate balance of temperature, pressure, and microscopic interactions. The quiet birth of clouds and the gentle descent of rain reveal the elegant dance of water in our atmosphere. Yet, the sky holds even more dramatic secrets, forces that can transform a gentle shower into a powerful spectacle. Our journey has explored the serene side of atmospheric wonders. But what happens when these processes accelerate, when the energy of the sun and the Earth's rotation combine to unleash something far more intense? Our next chapter explores the thunderous charge of storms. Our previous journey explored the gentle descent of rain, but sometimes the sky's energy escalates, transforming a soft shower into a spectacle of immense power. This transformation, from tranquil cloud to thunderous charge, held a deeper secret, one that captivated early natural philosophers. What fueled such a dramatic shift? For centuries, lightning and thunder were viewed with awe and fear, often attributed to divine wrath. Yet, a quiet curiosity began to stir, suggesting these phenomena might be governed by natural, understandable laws. To understand a thunderstorm, we must first recall the abundance of moisture. Just as with gentle rain, warm, moist air is the primary ingredient, but here, it is present in vast, concentrated quantities, rising rapidly. This leads to the second ingredient, atmospheric instability. When a parcel of warm, moist air is less dense than the surrounding cooler air, it will naturally continue to rise. This buoyancy causes it to accelerate upward, much like a hot air balloon ascending rapidly into the sky. This powerful upward motion or lifting mechanism is crucial. It can be triggered by various forces, the sun warming the ground and forcing air to ascend, or a colder air mass pushing warmer air aloft along a front. This initial push is the critical spark. As this unstable, moisture-laden air ascends, it cools and condenses, forming the familiar, towering cumulonimbus clouds. These structures are truly colossal, stretching many miles into the atmosphere and reaching immense heights, often piercing the upper troposphere. Crucially, as water vapor condenses into liquid droplets within these rising columns, it releases latent heat. This heat warms the surrounding air, making it even more buoyant, further fueling the powerful updraft. Inside these colossal clouds, a chaotic dance unfolds. Powerful updrafts and downdrafts churn, creating a turbulent environment where ice crystals, supercooled water droplets, and soft hail, graupel, coexist. This is where the freezing temperatures at higher altitudes become critical. Within these elevated regions, water droplets can remain liquid even when temperatures fall well below 0 degrees Celsius. They are known as supercooled water droplets, a curious state of matter. Within this icy realm, countless collisions occur. Lighter ice crystals are carried upward by the updrafts, while heavier graupel particles, which are essentially small, soft hailstones, fall downward. When these ice crystals and graupel particles collide, a remarkable phenomenon occurs, a transfer of electrical charge. The heavier graupel tends to gain electrons, thus acquiring a net negative charge during these energetic interactions. Simultaneously, the lighter ice crystals, having lost electrons, become positively charged. The powerful updrafts then carry these positive ice crystals to the upper regions of the cloud. This continuous process creates a distinct separation of charge within the thundercloud's vast structure. The top of the cloud becomes predominantly positively charged, while the base accumulates a large negative charge, setting up a massive electrical field. Below the negatively charged cloud base, the Earth's surface responds by becoming positively charged through electrical induction. This creates an enormous electrical potential difference between the cloud and the ground, a palpable tension building in the air. This immense electrical tension, meticulously built up through countless microscopic collisions and charge separations, sets the stage for one of nature's most dramatic and powerful displays: lightning, a sudden, brilliant discharge of accumulated energy. For millennia, lightning was seen as a terrifying and unpredictable manifestation of divine power. Humans could only witness its awe-inspiring fury, unable to grasp its true essence or its underlying natural principles. But in the 18th century, during the Age of Enlightenment, one mind dared to challenge this ancient belief. Benjamin Franklin, a polymath driven by insatiable curiosity, began to ponder the nature of lightning. Franklin observed similarities between lightning and the sparks generated by early electrical experiments. He hypothesized that lightning was not divine wrath, but simply a grand-scale electrical phenomenon. To prove his theory, Franklin conceived a daring and incredibly dangerous experiment. He would attempt to draw electricity directly from a thundercloud using a simple kite, a key, and a silken string. It was a perilous endeavor. In June 1752, during a Philadelphia thunderstorm, Franklin and his son launched a kite with a pointed wire at the top. A key was attached to the wet string, insulated by a silk ribbon held in his hand. As the storm passed overhead, a small spark jumped from the key to his knuckle, then another and another, accompanied by a faint crackle. It was subtle yet unmistakable proof of electricity flowing from the sky. This small, observed spark was a monumental breakthrough in scientific understanding. It confirmed Franklin's audacious hypothesis. Lightning was indeed a form of electricity, a natural force that could be studied, understood, and even harnessed. The demystification of lightning had profound implications. No longer a supernatural force, it could be tamed. Franklin's invention of the lightning rod soon followed, offering practical protection to buildings. The thunderous charge of storms, once a terrifying mystery, was now revealed as a powerful yet understandable release of atmospheric energy. It was a testament to the power of observation and daring inquiry. From the gentle hum of fog to the electrifying power of a thunderstorm, our journey through the skies has revealed layers of complexity. Yet, one more wonder awaits, often arriving after the storm's fury has passed, or when the air grows truly cold. Our next chapter explores the whisper of falling snow. Our last chapter plunged into the electrifying heart of storms. Yet, when the thunder fades and the air grows truly cold, another, more delicate wonder descends from the sky. This is the whisper of falling snow, a phenomenon of quiet beauty that has captivated observers for centuries. In the early 17th century, amidst the burgeoning scientific revolution, a keen mind named Johannes Kepler, renowned for his laws of planetary motion, found himself equally captivated by earthly geometry. His curiosity extended beyond the stars to the smallest, most fleeting forms of nature. One day, as snow fell upon Prague, Kepler noticed something remarkable about the snowflakes. not their infinite variety, but a common, underlying principle, their consistent six-sided symmetry. Every single flake, no matter how complex, seemed to adhere to this hexagonal pattern. Why 6? Why not 5 or 7 or a random assortment of angles? This question intrigued Kepler. He believed that such precise regularity in nature must stem from fundamental geometric principles, a divine order embedded in the physical world. In 1611, Kepler published a small treatise, A New Year's Gift, or On the Six-Cornered Snowflake. In it, he pondered the packing of spheres and the crystalline structure, making an early, intuitive leap towards understanding the invisible architecture of matter. Kepler's work marked one of the earliest systematic observations of crystalline forms. It was a profound shift, suggesting that even the most delicate and transient natural phenomena followed precise, mathematical rules, laying groundwork for future crystallography. But how did these intricate forms actually grow? The answer lies in the unique properties of water molecules and the conditions high in the cold atmosphere. Unlike rain, which often starts as liquid, snow begins its life as a direct transformation from gas to solid. This process is called deposition. When water vapor in a cloud encounters temperatures below freezing, it doesn't necessarily form liquid droplets first. Instead, it can freeze directly onto a tiny nucleus, often a microscopic dust particle or a pre-existing ice crystal. For this to occur, the air must be supercooled and saturated with water vapor. The colder the temperature, the more readily water vapor molecules will lock into place on a growing ice lattice, bypassing the liquid phase entirely. The first step is the formation of a tiny, six-sided ice crystal, a hexagonal prism. This shape is a direct consequence of the molecular structure of water. Hydrogen bonds naturally arrange water molecules into this specific, stable six-fold symmetry as they freeze. As the crystal falls through the cloud, it encounters varying conditions of temperature and humidity. These subtle changes determine how the ice crystal grows, adding more water molecules to its structure. This is where the intricate arms and branches begin to form. The arms grow outwards, often developing side branches, creating the familiar, elaborate patterns. If the crystal encounters a layer of supercooled water droplets, these droplets may freeze onto its surface, a process called riming, adding a frosty coating or forming graupel. Because each snowflake follows a unique path through the cloud, encountering slightly different temperature and humidity profiles at each moment of its descent, no two snowflakes are ever truly identical. Each is a fleeting, crystalline autobiography of its journey. To truly appreciate this diversity, one needed more than just observation. One needed to capture these ephemeral forms. This challenge was taken up by a self-taught scientist in Vermont, whose lifelong dedication would reveal the astonishing artistry of snow. Wilson A. Bentley, a farmer from Jericho, Vermont, lived in a place where snow was a constant companion for much of the year. From childhood, he was captivated by the beauty of individual snowflakes, determined to capture their fleeting perfection. Bentley initially tried to draw the snowflakes, but they melted too quickly, and his hand could not capture their intricate detail. He knew he needed a more precise method, something that could freeze time itself. His breakthrough came with photography. In 1885, after years of experimentation, Bentley successfully rigged a bellows camera to a microscope. This allowed him to photograph the delicate structures before they vanished. The process was painstaking. He would catch snowflakes on a black velvet tray, then quickly transfer a promising specimen to a glass slide using a fine wooden sliver or a feather. The cold was crucial. He worked in an unheated shed, often in sub-zero temperatures. Once on the slide, he had mere seconds to focus the microscope and expose the photographic plate before the crystal melted or sublimated. Each successful image was a triumph of patience and precision, a battle against nature's fleeting beauty. Over 46 years, Bentley took more than 5,000 snowflake photographs. His collection became an unparalleled visual catalog, revealing the astonishing diversity and complexity hidden within what appeared to be simple white flakes. He famously declared, "No two snowflakes are alike," a statement that, while perhaps not scientifically absolute, perfectly captured the essence of his findings. Each was a unique masterpiece, a testament to nature's infinite variations. Bentley's work, initially dismissed by some as mere amateur curiosity, eventually gained scientific recognition. His meticulously documented images provided invaluable data for meteorologists and crystallographers, proving the intricate growth patterns. His photographs validated the theoretical understanding of ice crystal growth, showing the delicate interplay of temperature, humidity, and atmospheric conditions that shaped each individual crystal as it fell. The whisper of falling snow, once just a seasonal event, was now understood as a complex dance of molecular forces, guided by the very geometry of water. It transformed a common weather phenomenon into a profound example of natural art and scientific wonder. From the invisible currents of wind to the quiet birth of clouds, and now the delicate artistry of snow, our journey has revealed the hidden mechanisms that shape our skies. But the atmosphere holds even grander, more dynamic systems, ones that bring together all these elements in a powerful global embrace. Our next exploration will delve into the vast, interconnected systems that orchestrate our planet's climate. Our last chapter explored the delicate artistry of falling snow, a singular wonder. But the atmosphere is not a collection of isolated events. It is a vast, interconnected system, a grand, swirling tapestry where every thread influences the next. The question now turned to how these individual phenomena wove together on a global scale. The scientists realized that parts of this atmospheric ocean acquired distinct characteristics. Vast bodies of air, sometimes thousands of miles across, would linger over specific regions, taking on their properties. Air masses formed over cold, snowy land became cool and dry. Those over vast, warm oceans became warm and moist. These air masses were like giant, invisible blankets, each carrying its own unique atmospheric signature, shaping the climate of entire regions. The most dynamic weather often occurred not within these uniform masses, but where they met. These boundaries, where air masses of different temperatures and densities converged, were named fronts, a term borrowed from military strategy, signifying a battleground in the sky. A cold front, where dense, cold air pushed under warmer, lighter air, created a sharp, steep boundary. The warm air was forced rapidly upward, leading to quick condensation and often intense but brief precipitation, sometimes accompanied by thunder. Conversely, a warm front saw warm air gently rising over a retreating wedge of colder air. This gradual ascent led to widespread, layered clouds and often prolonged, lighter rain or snow, blanketing vast areas with a steady, gentle fall. Sometimes, a faster-moving cold front would overtake a warm front, lifting the warm air entirely off the ground. This occluded front created complex, evolving weather patterns, a testament to the dynamic, three-dimensional interplay of our atmosphere. Understanding air masses and fronts transformed weather forecasting. It allowed meteorologists to predict not just isolated events, but the progression of entire systems across continents, seeing the atmosphere as a grand, moving tapestry, constantly weaving new patterns. While surface observations were vital, the atmosphere was a truly three-dimensional entity. To fully understand its movements, scientists needed data from above, far beyond what ground stations could provide, reaching into the upper currents of air. The answer came in the mid-20th century with the development of the radio sonde, instruments carried aloft by large weather balloons. These devices measured temperature, humidity, and pressure, transmitting data back to the ground as they ascended. By tracking the balloon's movement, scientists could also determine wind speed and direction at various altitudes. This provided the first comprehensive slices of the atmosphere, revealing the invisible currents and layers high above, layer by layer. Another leap came from wartime technology. Radar, initially designed to detect aircraft, proved remarkably adept at detecting precipitation. Radio waves bounced off raindrops and ice crystals, painting a picture of storms as they formed and moved. This allowed for real-time tracking of rain and snow, revealing the internal structure and movement of storms in unprecedented detail. The invisible downpours, once only felt, became visible on a screen, allowing for immediate warnings. But even balloons and radar offered only localized views. The true global perspective arrived with the space age. The launch of the first weather satellites in the 1960s revolutionized atmospheric observation, offering a vantage point never before imagined. From orbit, satellites provided sweeping, synoptic views of cloud patterns, hurricane formations, and vast weather systems unfurling across oceans and continents. The entire atmospheric tapestry was suddenly visible, a single, connected entity. This continuous global monitoring transformed meteorology from a regional science into a truly planetary endeavor. No longer were there blind spots over vast oceans or remote landmasses. The entire planet's atmospheric dance was now observable. The combination of surface stations, balloons, radar, and satellites generated an unprecedented flood of data. The challenge shifted from acquiring information to processing and understanding its immense, swirling complexity, a task beyond human capacity alone. The dream of predicting weather mathematically by solving equations that described atmospheric physics had existed for decades. Wilhelm Bjerknes in the early 20th century laid the theoretical groundwork, but the sheer volume of calculations was insurmountable. Imagine dividing the entire atmosphere into millions of tiny boxes. For each box, one needed to calculate how temperature, pressure, humidity, and wind would change over time, minute by minute. It was a task that would take thousands of human calculators years to complete for a single forecast. The solution arrived with the dawn of the electronic age. The first general-purpose electronic computers, like ENIAC in the 1940s, offered the raw computational power needed to tackle these complex atmospheric equations, performing calculations at speeds unimaginable before. In the 1950s, pioneering meteorologists working with these nascent supercomputers began running the first numerical weather prediction models. These were crude at first, offering only limited accuracy, but they represented a monumental step forward, a true scientific breakthrough. These models essentially simulated the atmosphere's future state. They took current observations, applied the fundamental laws of physics, conservation of energy, momentum, and mass, and calculated how these properties would evolve over hours and days. Over decades, as computers grew exponentially more powerful, and as scientists refined their understanding of atmospheric processes, these models became increasingly sophisticated and accurate, incorporating ever more variables and complex interactions. What was once a day of guess could now be predicted with reasonable accuracy several days in advance. The grand tapestry of global weather, once seemingly chaotic, was revealing its underlying, predictable weave, allowing humanity to prepare and plan. From the invisible pressure of the air, to the intricate dance of snowflakes, and now to the vast interconnected systems that span our planet, we have seen how patient observation and technological ingenuity have allowed us to unravel the atmosphere's secrets. Yet our journey is not complete. The interplay between weather and the long-term patterns of climate holds further mysteries, shaping our planet's future in ways we are only beginning to fully comprehend. Tonight, our journey through the swirling skies concludes. We began by questioning the invisible ocean above us, that vast, ethereal blanket we call the atmosphere. It was a realm once filled with myth, its mysteries whispered in ancient tales. But through centuries of quiet observation and persistent inquiry, the veil began to lift. Minds like Torricelli and Pascal dared to weigh the air itself, proving its tangible presence, its gentle, pervasive pressure upon our world. They showed us that this invisible ocean had depth, its pressure subtly shifting with every ascent, a measurable force that shaped our very existence. Then came the graceful dance of winds. From Halley's early maps to Hadley's cellular vision and Coriolis's mathematical elegance, we learned how the Earth's spin orchestrates grand atmospheric currents. These invisible currents, born of the sun's warmth and the planet's rotation, proved to be architects of climate, guiding moisture and shaping landscapes across continents. Our journey then brought us to the quiet birth of clouds, those ethereal sculptures of condensed vapor. We discovered the critical role of the dew point, that precise temperature where the invisible transforms into the visible. And we found the tiny, ubiquitous condensation nuclei, the unseen seeds upon which every cloud droplet forms, turning mere humidity into the sky's vast, swirling canvases. Luke Howard's patient classification gave us a language to describe these forms, allowing us to read the sky's silent messages, predicting its moods and intentions. From these clouds, we witnessed the gentle fall of rain, a marvel of microphysics. Whether through collision coalescence or the intricate Bergeron-Feindeisen process, tiny droplets grew into life-giving streams. And when the air grew cold enough, the whisper of falling snow revealed nature's exquisite winter art. Kepler's early insights into their six-sided geometry were later brought to life by Wilson Bentley's tireless photographic pursuit. Each snowflake, a fleeting, unique testament to the subtle interplay of temperature and humidity, became a crystalline autobiography of its journey through the clouds. Our journey then escalated to the thunderous charge of storms, those powerful releases of atmospheric energy. We learned how rising moist air, combined with freezing temperatures, creates vast electrical generators in the sky. Benjamin Franklin's daring experiment demystified lightning, transforming it from divine wrath into a fundamental electrical phenomenon, an awe-inspiring yet understandable force of nature. Finally, we explored the global weave, the grand tapestry of weather. Air masses and fronts, vast systems of interacting air, revealed the interconnectedness of our planet's climate. From radio sondes carried aloft by balloons to radar's watchful eye and the sweeping views from satellites, humanity gained new eyes to see the atmosphere in its magnificent entirety. The dawn of powerful computers allowed us to simulate this intricate dance, transforming weather forecasting from an art into a science, predicting the future moods of our sky. This entire journey from ancient wonder to modern understanding has been driven by a fundamental human curiosity, a relentless desire to unravel the world's secrets. It is a testament to patience, to careful observation, and to the occasional, exhilarating breakthrough that reshapes our perception of reality. The atmosphere, our living blanket, is a system of profound elegance and breathtaking complexity. It is a delicate balance, constantly shifting, yet governed by immutable physical laws. It is the very breath of our planet, nourishing life, sculpting landscapes, and inspiring awe with its ever-changing beauty and immense power. Our deep connection to the sky above us is undeniable. Every breath we take, every drop of rain that falls, every gust of wind that blows, reminds us of our intimate relationship with this atmospheric embrace. It is a reminder of how intertwined we are with the natural world, how the smallest changes in its delicate balance can ripple through our lives. As we gain a deeper understanding of its mechanisms, so too comes a shared responsibility to continue to observe, to learn, and to protect this vital, beautiful part of our home. The mysteries of the atmosphere may never be fully exhausted, new questions always emerging from the depths of our knowledge. But the journey of discovery itself is the true reward. And so, as the moon climbs high and the world settles into its nightly rhythm, may the whispers of the wind, the gentle hum of the clouds, and the quiet dance of the atmosphere bring you peace. Sleep well.